In the previous segment, we discussed about the deformation basically under the pure torsion of a shaft, and we came up with and then again I should draw the canonical configuration. So, this basically is our canonical configuration, uniform shaft, equal and opposite torque, length L. So, if this is the situation, then we had your gamma max, okay, gamma max, we said that it will be rho over C, sorry, in fact it is the opposite. Means your gamma is equal to rho over C times gamma max. Okay. So, that is what we had derived. Okay. So, what it means is if I draw this circle and this rho is the radius from this center rho, and the C is the maximum radius, right. So, that means if I draw like this, so this gamma increases from 0 when rho is 0, gamma is 0 to the maximum at rho equal to C, which is gamma max. Suppose this is gamma max, then it varies linearly like that. Okay. So, this is how we derived it, and now what we can do is let's multiply by G on both the sides. Okay. So, that will give us, so this is tau is nothing but again rho over C tau max. Okay. So, now the same distribution, or I should say similar distribution, just multiplied by with a constant which is the shear modulus. So, the variation of even tau also is like that, the same variation or at least the similar variation. Okay. In fact, if I tell the slope, it is the same. Okay. So, that is how it will vary, and with this, if you remember the, sorry, what I was doing, the previous slides where I had written, yeah, this is the expression I am referring to. So, we want to get a relationship between the applied torque and the distribution of the torque, and at that time we did not know how the shear stress is varying with distance or the radius, and now we have come to a stage where we have this expression with us which tells us that tau varies with rho in this way. So, now we can write the expression as the torque should be equal to integration of rho times tau dA over the full area. Now, in place of tau, we can simply substitute this to get tau max, which is a constant, over C, which is a constant. So, tau, when I say constant, what I mean is once you apply a torque in a given condition, the maximum stress which has been developed, that is a constant. Okay. and then integral it will be what, rho square dA over the full area. Okay. Now this term you should be familiar with. This is nothing but the polar moment of inertia. If I have a cross section like this, and if I take an area, elemental area dA, and its distance is say rho, now about an axis which is perpendicular to this plane coming out of the blackboard, and about that if I try to get the moment of inertia, so rho square dA is that moment of inertia if I integrate it. Okay. So that means this is generally written as J, represented as J, the polar moment of inertia, and then I should write it as tau, not this, tau max J times C. Okay. So that means I should write, in fact, instead of this, let me go to the other thing. So your torque is nothing but tau max J by C. Okay. Now, so in fact, how it is written always or most of the time is not in this form, but in the form like this. This is T C over J, because it's almost always assumed that the torque is applied, this torque is applied on the shaft which has these geometric properties of maximum radius C and polar moment of inertia J, and the torque or the stress, the shear stress, which will be developed at maximum value, that is on the surface of the cylinder. So that will be of this value. Now if this is known, then we can always write tau to be T times rho over J, because we know that tau also varies like rho over C times T max. So that from there we just write like this. Okay. So this is the variation of torque, stress, shear stress. See, here we had got a variation of the stress, but that was expressed in terms of the maximum stress that is developed. Means in a way, this was also not known in terms of the externally applied load. Okay. This is just a variation with expressed in terms of maximum value which has developed. But now here we have written the variation of tau with the radius rho, but this is expressed in terms of the externally applied torque T. So that means now if we applied a torque T, the stress which will be developed will vary like this, and which will reach to a maximum value of tau max, which will happen on the surface. So that's about the stresses which will develop on a cylindrical shaft once it is subjected to a equal and opposite torque, that is the pure torsion. Now there is one important observation which we should make, and that is like this. Suppose I draw the side view of the cylinder, and in fact here you have applied the torque maybe, and just consider an element on the surface, a small element on the surface of the cylinder. Okay. Now, we know that the shear stresses will be, acting. So, I would do one thing. So, I'll just replace like that. Okay. Now, so the shear stresses which will be developed on the surface will look like this, right? The tau max basically, because on the surface if we see the maximum value of the shear stress will be developed and they will look something like that, and then if we take an element of this orientation, obviously there will be no other stresses, like normal stresses will not be there, because we had discussed that on all the surfaces parallel to the or perpendicular to the axis, you can say, the only stresses which are there are the shear stresses, and even in the axial direction these stresses will be there. But now we have discussed under our stress transformation that if now I take an element which is at 45-degree angle with respect to this original orientation, then what will happen is I will reach a stage where I will have only normal stresses, because that is the direction of the principal or the principal planes. If you want to just talk in terms of Mohr's circle, now suppose this is my starting point of drawing the Mohr circle. So there is no shear, normal stress. So my first point will be, say, somewhere here, that is 0 and say minus tau xy, and similarly here it's say 0 and tau xy, and then I will just draw the circle with this being the diameter. So this is the Mohr circle, and then I get the not this. Okay. Now this is my maximum and this is my minimum stress, normal stresses, and they are at an angle of, see, this angle is 90-degree. That means there, if I turn by 45-degree, so now if I draw like this, so, and now this angle is 45-degree. If I turn my elemental square by 45-degree, I will reach the place where I will get the maximum tensile normal stress, and that can be shown like this. So that normal stress will be like this, tensile. On the other side, it will be the same value of compressive stress. Okay. Now, so I should draw both the way so that it will be clearly printed in the mind. Okay. So that's how the stress transformation can be seen using the Mohr circle. So that means if I consider an elemental square like this, the state of stress is a pure shear. And now if I just turn by 45-degree, I will go to a state of stress where in two direction or in one direction it is a pure axial tensile force, and exactly 90-degree to that it is a purely compressive normal stress. So this is that compressive one, this is the tensile one. Now if you remember, I discussed about the breaking of a chalk at a particular angle, remember? So that can now be explained properly with this concept. See this. At that 45-degree angle, you are having tensile forces, right, which are acting like this, and to that 90-degree it's compressive. And the chalks, so they are brittle materials, and brittle materials, they are very weak, in tension, but they are very strong in compression. Okay, like concrete also, you might be knowing that concrete is really very weak in tension, and that is why they reinforce it with steel rods so that it will gain tensile strength. Otherwise, the concrete strength is actually in compression. Okay, so in fact the strength that they mention on the cement packets, so they mention the compressive strength of a concrete block, okay, under certain conditions. Now, but the tensile strength is very low for them, any such brittle materials. Now, exactly the same thing happens here. So that means the chalk actually is very weak with respect to the pull that gets applied in this direction, but it is very strong to the push that gets applied in this direction. And now you see that these kind of pulls have resulted in by applying these torques, right. So these torques we apply, we didn't apply any pull or push, we just applied a twist by using this torques, and from there in a particular direction, that is 45-degree angle, the tensile stress got developed and the material is weak under tension, so it fails at that 45-degree angle sections. So that basically explains why that chalk broke at a particular such shape. Yeah, so that's what I think is about the stress field in under the pure torsion case. Okay, and yeah, one more point. If if I have any space, let me go to the other page. So see, for the complete circular shaft, we saw that the stress field behaves like this, it changes linearly. So this is a tau max and it varies like that, right? So something like this. So you can put the arrows like that to just, okay. Now the same thing can be drawn for an annular shaft, because we said that any cross section which is axisymmetric, for that or all the discussion which we had, they work, okay, they are valid for that. So now suppose we have an annular hollow shaft, then the stresses will be like this. Now from here the variation will be exactly in the same way, but there will be no stress here because there is no material. So we can just if this is the maximum tau max, and we can just do like that, and at here, sorry, you have this variation. So this is the portion where the stress field will exist, and it will vary from a minimum value which is not 0 now, tau min, to tau max, whereas here the minimum value was 0, which was at the center. So that should be kept in mind for solving the problems. And one more thing, the J values, okay, so they are like, the pi d to the power 4 over 32, if I remember correctly. So for a solid shaft, and if you go for this, this is like, so d outer 4 minus d inner fourth power. So that's the thing we should keep in mind, and then you can solve the problems of stresses under pure torsion. Okay, so we will again in the next segment we will meet and discuss about the deflection. Okay, though we talked about the strain from where we came to the stress field, we will see something more about the deflection, the final thing, and then we will talk about how we can see this kind of a pure torsional case as a torsional spring also. Okay, so see you in the next segment.